Hey everyone, this is Morgan. So we're continuing on with this titration math. We're on page 13 of the Ionic Solutions lecture for AP Chem. And what we're doing is we're titrating 20 milliliters of 0.1 molar acetic acid with 0.1 molar NaOH. And we want to measure what the pH is or calculate what the pH should be at each of these points. Now before we start, all we have is a weak acid, which means we have HA plus H2O, which gives us H3O plus and A minus, and we're going to do an icebox here, and this is 0.10, and we'll ignore the water, 0 and 0, minus X, plus X, plus X, 0.10 minus X, X and X. So my Ka for acetic acid is 1.75 times 10 to the negative fifth, which is going to equal, based on this, x squared over 0.10 minus x. That's one that I can approximate. When I go through and I've solved this whole thing, x is going to equal 1.32 times 10 to the negative third, which is equal to the H plus concentration. So the pH is equal to the negative log of 1.32 times 10 to the negative third, which equals about 2.88. I've seen some calculators round it as 2.89. Don't worry about that. Okay, so that's before any addition of base. Now, let's think about this. Acetic acid, some hydroxide, when they react, will make water and some acetate ion. So as long as I have both acetic acid and acetate ion present, I'm going to have a buffer. And I can treat this as a buffer situation. So HA plus OH minus gives me H2O and A minus, and when I have a buffer, the pH equals the pKa minus the log of the HA over A minus. Okay? The pKa is the negative log of 1.75 times 10 to the negative fifth, which comes out to be 4.76. Okay, now let's kind of do an icebox here. I'm starting off with 0.1 times 20.0 milliliters, or 2.0 millimoles. The hydroxide is 2 milliliters times 0.10 molar NaOH, or 0.2 millimoles. Minus 0.2, minus 0.2, none there. 1.8 millimoles here. Now I can ignore the water. That starts out as 0, but this is plus 0.2. So that leaves me 0.2. So the pH equals 4.76 minus the log. Now the amount of HA is 1.8 millimoles. The amount of A minus is 0.2 millimoles. They're both divided by the same volume, so that cancels out. That's cool. And this equals 3.81. So what happened was the pH shot up because I added some base to a weak acid, and it should. That makes perfect sense. Now the next few answers are going to be a little more interesting. Now what happens after I've added 5 milliliters? Okay, well, adding 2 milliliters, I went up by a whole pH point. We got to remember, it starts to buffer after I've added some here. This is in the buffer region, okay? Okay, so now pH equals 4.76 minus the log. Okay, so I start off with 2.0 millimoles. This time it's 0.5 of the base, so that means this is a 1.5 and this is a 0.5, and that equals 4 0.28. So I've added more than twice as much base as I did in this previous question, and this time I only went up half a pH point instead of a full pH point. Well, that shows you it's buffering. Okay. Now, when I've added 10 milliliters, this is actually the midpoint, or the half equivalence point, or the halfway point, just depending upon what language skills you want to be using. pH equals 4.76 minus the log. And this is where this is 1.0 and this is 1.0. I started out with 2.0 minus, it'll be minus 1.0 this time. That leaves me with 1 and 1. Hey, that equals 4.76, but I already knew that because at the midpoint, the pH is equal to the pKa. All right. Now, as I'm getting very near equivalence here, you'll notice those weren't big jumps. It's going to start to be a bigger jump now because we're near the equivalence point. pH equals 4.76 minus the log. Now let's check this out. I started out with 2.0 minus, and the amount of base at this point is going to be 1.9, which means I have 0.10 of the HA left, and I have 1.9 of the A minus left, and this comes out to be 6.04. Okay, that's a bigger jump now, and in my next jump, it's going to shoot up a lot because it's going to stop buffering. So, 2.0 minus 2.0, there's no HA left, which means what's left is A minus. Okay? And I have 2.0 millimoles of A minus divided by a total of 40.0 milliliters, which equals 0.05 molar A minus. The A minus will react with water. It will form HA and OH minus. I can do an icebox. 0.05, ignore. 0, 0, minus X, plus X, plus X. 0.05 minus X, X and X. So X squared over 0.05 minus X equals, and here's a really important point, it equals Kb, not Ka, because it's hydroxide over here. So I can find the Kb by taking Kw, 1.00 times 10 to the negative 14th, and dividing by Ka, 1.75 times 10 to the negative 5th, and that equals 5.71 times 10 to the negative 10th. I can approximate this because K is so small, and it turns out that X is actually going to equal 5.35 times 10 to the negative 6th, and that's the hydroxide. So my POH equals 5.28, and my pH equals 8.72. And I do actually know that the pH should be above 7 when it's a weak acid, strong base titration. All right. Let's look at a place now that is after the equivalence point. This was equivalence. This was just near the equivalence point. What if I just have some excess hydroxide? Well, okay. I have 2.1 millimoles of hydroxide minus 2.0 millimoles of H+. That's 0.1 millimoles of hydroxide. Divide that by 41 milliliters. The milli cancels. This equals 2.44 times 10 to the negative 3rd molar. So the POH equals the negative log of that, which is 2.61. Subtract that from 14, and the pH equals 11.39. And that actually makes sense. It should be a pretty high pH because the only thing determining the pH at this point is the excess hydroxide ions. All right, we've still got one more of these to go. We'll take a look at a strong acid, weak base titration next. Thanks for tuning in. This is Morgan signing off.